Here's a problem that I'm going to do two different ways to illustrate the importance of defining a system. So we have a block that's pushed against a spring with spring constant K. It's pushed a distance x, and then it's released from rest. It slides across a frictionless surface and moves up a ramp of height h. And the question is, what is its velocity when it's at the top of the ramp? So the first way that I'm going to do it is I'm going to define my system as just the block. Okay, so in that case, the only energy that the block can have on its own is just kinetic energy. Right, so E1 is going to be equal to the kinetic energy at the beginning, and because it's released from rest, that's 0. And then E2 is going to be the kinetic energy at the top, and that's 1/2 mv squared. Okay, so then our change in kinetic energy, or in this case, our change in energy, is equal to the net work that's done on the block, and that change in energy is going to be the change in kinetic energy. Okay, so what forces are doing work on the block? Well, that's going to be, we've got the spring that's doing positive work, and we've got gravity that's also doing work. Right, so the spring is going to do positive work 1/2 kx squared, and gravity is going to do work of negative mgh. Right, and that's going to give me the change in kinetic energy, which is the final minus the initial, and that's just 1/2 mv squared, because the initial kinetic energy is 0. And at this point, I've done all the physics. I can do the algebra to solve for the final velocity. Okay, now I'm going to do the same problem, but I'm going to define my system as broadly as I can. So my system is going to be the block, spring, earth system, which means now I can include the spring potential energy and the gravitational potential energy. Okay, so again, I have that the change in energy is equal to the external work, but because there's no friction or any other external forces, that's 0 in this case. Right, so that means that my change in energy, which is equal to, let's call this E2, 0.2 and that 0.1, right, so that's E2 minus E1, that's equal to 0. So what that means is that I have E2 is equal to E1. Right, so the energy in this system is conserved because there is no external work on it being done on it. Right, so now I can say, well, what is my energy at 0.1? Well, I could have kinetic energy, I could have potential energy from the spring, and I could have gravitational potential energy. Now, the kinetic energy is 0 because the block starts at rest. The potential energy due to gravity, I will define potential energy due to gravity as 0 at the lowest point. That's convenient. So in that case, that goes to 0. So my energy at 0.1 is just potential energy from the spring, which is 1/2 kx squared. And then my energy at 0.2 is, well, I could write down all of the forms that are possibly involved. So kinetic energy, potential energy from the spring, and potential energy due to gravity. Now in this case, the potential energy from the spring is 0 because the block is no longer contacting the spring. And I have the kinetic energy is 1/2 mv squared, and the potential energy due to gravity is mgh. Right, so now E1 is equal to E2, so I can set those two sides equal to each other. So I've got 1/2 kx squared is equal to 1/2 mv squared plus mgh. Okay, so if you compare that to the equation that we got before, we can see that they're mathematically equivalent. We've just moved the terms to different sides. Right, so either one of these can be solved for the final velocity, and you would, you would get the same algebraic expression, and if we had numbers, we would get the same value.